So welcome again. We start with a new lecture number 33 in this course on phase equilibria. So we'll first recap the contents of last lecture. So in the last lecture we discussed things like so basically we were looking at non-ferrous alloys, their phase diagrams, and what sort of microstructures that one can evolve. And then this is what we discussed 2-3 lectures back. In the last lecture we basically looked at measurement of or construction of a phase diagram. Basically by experimental means. So the tools to do that is, one is to carry out the thermal analysis, which is basically drawing time versus temperature plots for various compositions, and then stitch together the points representing start and end of solidification or melting. Okay. And the second aspect of this was to carry out other measurements, such as you can do dilatometry by looking at the change in the volume. You can do resistivity measurements, because resistivity changes as a function of composition as well as temperature, and it is particularly useful in solid state. And then you can do magnetization measurements. So these are basically, you can say, the last two are basically indirect measurements, and thermal analysis is a very good method, and this is all have to be accompanied by change in microstructure, by you have to examine this by optical and scanning, electron microscopy, as well as XRD, X-ray diffraction. So basically you have to examine composition, microstructure and phase analysis to correlate the results of time and temperature dependent phase transformations with the results of thermal analysis as well as resistivity, magnetization or dilatometry measurement. So all these put together can give you construction of a phase diagram of a given material. Now what we are going to do in this lecture is, we are going to just take up a problem of suppose you are given certain amount of data, and how can you construct a phase diagram. So essentially a problem solving in that sense. So let us look at, so it's a problem basically. The problem statement is, you have consider two elements, let us say lead and magnesium. Okay. Now data that is given is, first you are told that at 470 degrees centigrade you form a compound PbMg2 liquid of composition 80 atom percent magnesium and beta phase of composition 92 atom percent magnesium are in equilibrium. Another data that is given is, at 250 degrees centigrade, alpha phase with 10% magnesium. So when I say percentage, it is atomic percent in this problem. Liquid phase of composition 20 atom percent and PbMg2 phase are in equilibrium. Then we have third scenario, at room temperature, maximum solid solubility of magnesium in lead is that is alpha phase is 2%, and that of Pb in beta Mg is 1% lead, that is 99% magnesium. And then another data point that is given is melting point of lead is 327 degrees centigrade, melting point of magnesium is 650 degrees centigrade, and PbMg2 has a melting point which is 550 degree centigrade. Now, if this is the data that is given to you, how will you go about constructing a phase diagram? So, let us do that. So, let us first see. So, we see that if you look at the first data point at 470 degrees centigrade, the compound Mg2, which has atomic, which basically means 66.7% magnesium atom percent wise, liquid of 80% magnesium and beta phase of 92% magnesium are in equilibrium. So, this is basically 3-phase equilibrium. And now 3-phase equilibrium in binary phase diagrams happens occurs on a invariant line, which means now if I draw the line now, so let us say this is the line. So, let us first draw the extreme points. So, you have liquid phase of 80% Mg, beta phase of 92% Mg and PbMg2, which is essentially 67% Mg. Okay, let us say it's 67 instead of 66.7. So, this is at temperature 470 degree centigrade. So, if I mark these points, let us say this is, so highest point is 92%. So, this is 92%, lowest point is 67%. So, this is percentage Mg, and then in between somewhere we have 80% magnesium. So, we have liquid of composition 80%, okay, PbMg2 of composition, this is solid phase, and beta phase of composition 92%. So, if you have such a, now beta is also solid. So, if you now, based on the knowledge of phase diagram, we know that if liquid composition on this invariant line lies in the middle, okay, and there are two solids on either side of lower and higher composition, then we know that this reaction is nothing but liquid of 80%, because liquid is a high temperature phase, converting into PbMg2 solid plus beta solid of 67% and 92%. And we know that this reaction is eutectic. So, essentially what it means from the given data, that at 470 degrees centigrade, your liquid of composition 80% has given rise to two solid phases, beta and PbMg2, and whose compositions are 92% in beta and 67% in magnesium. So, this is a eutectic reaction that happens in lead magnesium phase diagram at 470 degrees centigrade between compositions 67 to 92%. So, this is first piece of information that we have derived. Second piece of information is at 250 degrees centigrade we are given. So, I again draw a horizontal line. So, this is at 250 degrees centigrade. Next, so it says that alpha phase with 10% magnesium, liquid with 20% magnesium, and PbMg2, which is with 67% magnesium, they are in equilibrium. So, liquid, so alpha I have with 10% magnesium solid phase, PbMg2 with 67%, and then liquid somewhere in between is at 20%. So, this again seems to be a eutectic reaction. So, this is again a eutectic reaction where liquid of composition 20% transforms into alpha phase of composition 10% plus PbMg2. This is again, both of them are solid phases. So, again a eutectic reaction that takes place. Now, the third data point was the solid solubility. So, which means at room temperature, if I draw the horizontal line, so let us say this is Pb, this is pure Mg, this is percentage Mg, atomic percent. So, it says that at the maximum solid solubility of magnesium in alpha, that is alpha lead, is 2%. So, somewhere at 2%, this is, you can say, C naught in C alpha naught, and this is the maximum solid solubility of lead in magnesium is 1%, that is 99%. So, this is C alpha C beta naught. Okay. So, beta phase is basically magnesium rich, it contains only 1% lead. Alpha phase is lead rich phase, which contains maximum of 2% magnesium at room temperature. So, now let us join these pieces of jigsaw puzzle. So, let us say, so I draw this phase diagram here. So, let us say this is percentage magnesium, this is Pb, this is Mg, right. So, somewhere in between we have 50. So, let us say 10, 20, 30, 40, 50, 60, 70, 80, 90, and we can remove this line a little bit to the left. So, let us say this is 100. So, if I draw a vertical line, it is going to be something like this. So, this is 100% magnesium, this is 100% lead. So, this is 10, 20, 30, 40, 50, 60, 70, 80, 90 and 100% magnesium, okay, and this is atom percent magnesium. On the y axis we have temperature, we have the maximum temperature of 650 degrees centigrade. So, let us say this is 100, 200, 300, 400, 500, 600, 700, okay. So, 100, 200, 300, 400, 500, 600 and 700 degrees centigrade, okay. Now, what I am going to do now is just to superimpose the previous information. So, the previous information was that first at what temperature? At 470 degrees centigrade, which is somewhere here, okay. So, 470 will be somewhere here. So, let me draw a horizontal line here, 470 degrees centigrade, okay. So, at 470 degrees centigrade we said that, so we draw a few critical points. We know that magnesium PbMg2 has a composition here. So, this is the composition of PbMg2, okay. So, this is PbMg2, okay, 67%. So, what we are saying is at this temperature PbMg2 92% of beta with 92% of magnesium. So, let us say 92% is somewhere here, okay, and then liquid of composition 80%. So, we say 80% is somewhere here, let us say this is 80%, all right. So, this is 80%, this is 92, this is 67. So, this is invariant line, the eutectic line. So, at this point you have liquid, at this point you have Mg2 Pb, and at this point we have beta. All right. Second information is at 250 degree centigrade. So that is at 250 degree centigrade. So let me draw 250 horizontal line at 250 degree centigrade. So we say that at this temperature you have alpha phase of composition 10%. So this is alpha phase of composition 10%. We have liquid of composition 20 atom percent. So this is liquid of composition 20 atom percent, and we have PbMg2, they are in equilibrium. So we have this as a tie line, okay. And then we have maximum solid solubilities. We can mark them. So 2% magnesium in lead is somewhere here. So this is 2%, and then we have 1% lead in magnesium, which is somewhere here. Okay, so this is C alpha naught, and this is C beta naught, and then we need to mark the melting point. So we say that the melting points of lead is somewhere here, which is 327 degree centigrade. So this is melting point of lead. So this is TM Pb, and the melting point of magnesium is 650 degree centigrade. So which is somewhere here. So let me just draw a line, horizontal line on this point. So this is the TM Mg, and then melting point of PbMg2, which is a line compound. Line compound means it has a single composition and it has a fixed composition. So its melting point is 550 degree centigrade, which is somewhere here. Let's say somewhere here. Okay. So this is TM PbMg2. So now we have to draw the boundaries to construct this phase diagram. So we know that in the eutectic you have, so obviously eutectic is going to look something like this. And this compound is a line compound. So as a result, this does not have any two phase region, it is a single phase line. So you connect this point with this point, this point with this point. So when you connect these points, you construct a phase diagram which has two eutectic reactions. So this is the first eutectic reaction, alpha liquid and Mg2Pb. So this is liquid region, all of it. Somewhere here you will have liquid plus alpha. This is alpha. This is liquid plus Mg2Pb. This is alpha plus Mg2Pb. And this is liquid plus beta. Here you have beta region. This is liquid plus Mg2Pb, and this is beta plus Mg2Pb. So this is how you have a phase diagram. Basically you can see it is a phase diagram which consists of two regions. The first eutectic between alpha and lead and Mg2Pb. Second is the eutectic between Mg2Pb and Mg. So you just put them together to construct a bigger phase diagram between lead and magnesium, and this is separated by a line compound Mg2Pb, which is like a component. So it is like a two binary systems you have put together. Okay. So this is the sharp phase boundary that you have because of presence of line compound. Okay. So I would suggest you to do some homework problems along the similar lines. So I would say, so your homework could be attempt problems related to phase diagram construction, and one of the books I can recommend is I would say Material Science and Engineering by V. Raghavan, and in that there is a chapter on phase diagrams. So attempt those problems. So this is something that you could find useful to construct a variety of phase diagrams. Now using this information you can attempt a few more questions. So we have drawn the phase diagram between lead and magnesium. So let us say the first thing somebody asks, if there is a question, let us say there is a question that what is the immediately after the completion of reaction, immediately after the completion of invariant reaction in an alloy with composition, let us say 40% magnesium. So calculate the phase fractions, for instance. So when you go to 40% magnesium, so this is 40% magnesium. So let us say we draw a vertical line. So 40% magnesium lies on the left hand side of the phase diagram. So what you do here is, what you see here is, first you have a liquid phase. This liquid phase converts into liquid plus Mg2Pb. So you have some crystals of Mg2Pb starting to appear. When you reach this point just before the invariant reaction, you have liquid and Mg2Pb whose proportions can be determined by lever rule. And then when you cross over this line, the liquid converts into eutectic mixture of alpha and Mg2Pb. So you will have Mg2Pb as a pro-eutectic phase followed by formation of a eutectic of alpha and Mg2Pb. So if you want to determine the, so for example, what is the proportion of pro-eutectic Mg2Pb at, let us say, so eutectic temperature is, I am saying, is at this composition the eutectic temperature is 250 degrees centigrade. So let us say at 249 degrees centigrade. Okay. So at 249 degrees centigrade, percentage pro-eutectic PbMg2 or Mg2Pb, this is nothing but the alloy composition 40 minus the solid solubility at that point, which is the alpha composition 40 minus 20 divided by 67 minus 20 into 100. So essentially it is this line. Okay. So you have 20, you have somewhere here you have 40%, this is 67%, and your eutectic lies at a composition of 20%. So this is eutectic, and your alpha will be, so this is eutectic composition Ce, this is Mg2Pb, and your alpha phase has a composition of 10%. So this is 10%, that is alpha point. So pro-eutectic Mg2Pb at this point for this composition, so this is C naught. So this is the percentage of pro-eutectic, which is roughly 42.5% atom percent, mole percent you can say. So because the compositions are given in atom percent, what you can determine is only atom percent or mole percent things. You cannot determine weight percent from this. So you will have to convert the atom to weight percent to achieve that. And then you can determine the eutectic Pb, eutectic Mg2Pb, that is total of PbMg2 minus of pro-eutectic PbMg2. So let me write it PbMg2 just to be consistent, and here also we can write PbMg2. So now what is total Mg2Pb? So total PbMg2, I am just keep on writing this, which is nothing but 40 minus 10 divided by 67 minus 10. So this is total out of alpha and PbMg2 present. So this is into 100, this is equal to 52.6. So, eutectic Mg2 PbMg2 rather is equal to 52.6 minus 42.5, that is nearly 11%, 10.1%. Okay. And likewise, you can determine the alpha phase. Alpha phase is nothing but total PbMg2. So, it is like 100 minus 52.6. This will be equal to 47.4% will be the alpha phase. So, this is how you can find the phase fractions in eutectical information. So, if somebody, you can also calculate what is the fraction of PbMg2 in eutectic mixture. So, if you want to find out what is the PbMg2 fraction in eutectic mixture, then this is going to be equal to 20 minus 10 divided by 67 minus 10 into 100. So, this is how you are going to determine the. So, you have a eutectic line which is alpha is 10%, this is eutectic composition 20%, this is the alloy composition, and this is the PbMg2. So, you will have at this point alpha plus eutectic, at this point you will have PbMg2 plus eutectic, and the total amount of PbMg2 in eutectic can be determined by so let me just, so the microstructure is going to look like this. So, you have pro-eutectic Mg2 phase, and then you have eutectic, this is eutectic. So, this is Mg2 Pb pro-eutectic, and this is eutectic. All right. So, if you want to determine the so you know what is the eutectic, so you have determined what is the Mg2 Pb proportion total, Mg2 Pb pro-eutectic. So, total minus pro-eutectic will be Mg2 Pb within the So, that is how you can determine the proportions. So, this is what we have discussed in this lecture. So, we have discussed basically how to construct a phase diagram from the given set of data. So, basically it is a problem solving. So, I would recommend you to, so essentially what you need to do is that you first need to identify what are the invariant reactions that occur and what are the various solids. So, you first determine the invariant reactions and the terminal points, and then looking at the knowledge of your invariant reaction, you need to basically connect various phase boundaries by connecting the terminals, and that is where your understanding of phase diagram comes into picture and invariant reactions. So, if for practice you should do the problems given at the back of chapter on phase diagram in Raghavan's book on material science and engineering. So, you should do that to achieve a better knowledge of how to construct phase diagrams. So, we will finish here. Thank you very much.